A transformer is a piece of equipment that changes the characteristics of electrical energy from one electric circuit to another using induction or magnetism. A distribution transformer is a component of an electrical distribution system that increases or reduces the voltage, commonly referred to as stepping up or stepping down the voltage. There are many different types of distribution transformers used throughout electrical distribution systems and the utility grid. These transformers typically fall into two categories, liquid-filled or dry-type. Liquid-filled transformers have coils that are immersed in insulating fluids such as mineral oil or natural ester fluids. These fluids provide good electrical insulation and carry heat away from the core and windings by convection. Fans can be added to dissipate more heat and achieve a higher power rating. With a dry-type transformer, the coils are constructed in a gaseous or dry insulation medium. Natural or fan-assisted convection of the air through the ventilation openings is used to dissipate heat. While the insulating medium is different, the basic concept of winding conductive material around a core and using a magnetic field and winding ratios to induce a different voltage remains the same. Utilities generate and transmit large amounts of power at high voltages using transformers to systematically decrease the voltages through substations as the electricity gets closer to the load. These utility-owned transformers are typically liquid-filled given their size and voltage requirements. In this video, we're going to focus on low-voltage dry-type distribution transformers, which can be commonly found in industrial and commercial applications as the electrical power gets distributed closer to or at the end load. Transformers use magnetism or magnetic flux to step up or step down a system voltage. This magnetic field is created by winding a conductor, known as the primary winding, around an iron core and passing electrical current through the windings. If you had another set of conductors, known as the secondary winding, wound around that same iron core, you could use the magnetic field to induce power through those windings. Note that the primary winding and the secondary winding are fully isolated from each other, meaning that they do not make any physical contact. These windings are referred to as the coils of a transformer. The term used to describe the number of times the coil is wrapped around the core steel in each winding is turns. Typically, the number of turns that the primary coil is wrapped around the core steel will be different than the number of turns that the secondary coil is wrapped around the core steel. Comparing the primary turns to the secondary turns will provide you with the turns ratio. The turns ratio determines the voltage that will be induced on the secondary winding for a given voltage that is applied on the primary winding. If the turns ratio is 4:1 and the primary voltage is 480, the secondary voltage will be 120 volts. This would be an example of a step-down transformer. If instead the number of turns on the secondary winding were to be greater than the number of turns on the primary winding, then the transformer would be a step-up transformer. The number of coils in a transformer will depend on whether the transformer is designed to be used in a single-phase or three-phase power system. In addition to using the turns ratio to determine the desired output voltage on the secondary, transformers must also be designed with the amount of output power in mind. This will determine the size of the transformer as well. The size of a transformer, or its power rating, is given in volt amps or VA. Most distribution transformers are rated in kVA or 1000 volt amps. The kVA rating of a transformer will be based on the load. Based on the kVA and knowing the voltage, you can calculate the rated current for the transformer primary or secondary. For example, a 75 kVA three-phase transformer with a 480 volt primary and a 208 volt secondary would have rated primary current of 90 amps and secondary current of 208 amps. Primary voltage, secondary voltage, number of phases, and kVA size are the starting pieces of information that are required to properly select a transformer. Now that we are more familiar with these terms and their meanings, let's look at the individual components that make up a low voltage distribution dry-type transformer. Here you see a transformer with the enclosure removed, commonly referred to as the core and coil assembly. This image is a three-phase transformer as evidenced by the 6 individual coils, one for each phase on the primary and secondary. The core steel is found inside of each coil. The secondary winding is wound around the core, followed by the primary winding. Each winding is surrounded by an insulating material to protect the winding and keep them fully isolated from making contact with themselves or the core steel. The end of each winding is then brought out to bus terminals, which are mounted in a horizontal row onto a terminal board. These terminals provide the connection point for incoming cables on both the primary and secondary of the transformer. A three-phase delta power connection will include 3 terminals, while a three-phase 4-wire Y power connection will include 4 terminals. One set of terminals is connected to their windings through the small black cables seen here, known as tap cables, as they are connected to the transformer taps. Taps are the term used to describe multiple possible connections to a specific winding. This unit has primary taps that are connected at various points in the primary winding. By moving the cables and connecting to different taps, an end user can manipulate and change the transformer's winding ratio. Taps are an important component within a transformer as they allow the user to achieve their desired secondary voltage given an inconsistent or undesirable primary voltage. Let's look at an example where taps could come in handy. This transformer, designed for a 480 volt primary and a 208Y 120 secondary voltage, has 7 possible tap connections to the primary winding. The transformer nameplate has a tap diagram showing these 7 possible connections and their associated voltages. It has 2 taps above nominal and 4 taps below nominal. The transformer is shipped from the factory with the terminals connected to tap 3, or the 480 volt nominal tap. This is known as the center tap, or the tap that represents a connection to the design or standard turns ratio for the unit, which happens to be 4:1 in this example. In our scenario, the customer's desired output voltage is the same as the nameplate secondary voltage, which is 208Y 120. However, the incoming primary voltage is higher than the nominal, consistently measured at 491 volts, yielding a greater secondary voltage than desired. In this scenario, the customer should reconnect the primary taps from tap 3 to tap 2, adjusting the output voltage closer to the intended 208Y 120. There are other terms and design characteristics that are important when selecting the right transformer and understanding how it will perform for your application. Frequency. It is important to understand the system frequency at which the transformer will be installed. In the United States, most electrical systems operate at a frequency of 60 Hz. However, there are specialty applications where other frequencies may be used. For frequencies outside of 60 Hz, a possible derating or a complete redesign of the transformer may be required. Impedance. The impedance percentage is the measure of the voltage drop when the transformer is at full load due to the winding resistance and leakage reactance expressed as a percentage of the rated voltage. Impedance is denoted as %Z or simply Z. Sometimes impedance is incorrectly confused with resistance. The impedance value of a transformer will always be listed on its nameplate as a critical value to be known, especially when conducting short circuit and coordination studies for an electrical system. Increasing the impedance of a transformer will reduce the amount of available short circuit current downstream. However, higher impedance values could result in more voltage drop, poor voltage regulation, and lower efficiency. Temperature rise in a transformer refers to the maximum temperature that the transformer's internal insulation can reach above the ambient temperature during normal operation. The standard temperature rise for a low voltage dry type transformer is 150 C or 150 Celsius. There are other optional temperature rise values available, with the most common options being 115 C or 80 C. To understand temperature rise a bit more, let's look at a ventilated transformer example. Ventilated transformers have an insulation class that is rated for 220 C. There are harmonized design standards that require designs based on 40 C ambient temperatures that also allow for a hotspot temperature rise of 30 C. This 30 C can be thought of as a safety factor to allow the transformer to run beyond its rated kVA for a short period of time. Therefore, 40 C ambient plus 30 C hotspot plus 150 C temperature rise above ambient equals 220 C. This shows the math behind a standard transformer with 150 C temperature rise. If we take the same transformer and design with a 115 C temperature rise or an 80 C temperature rise in mind by adding additional conductive material and hold the same ambient and hotspot requirements, we will have a transformer that has additional capacity available in case there is a need to overdrive the transformer beyond its nameplate kVA. 115 C temperature rise design units have 15% additional capacity, and 80 C temperature rise units have 30% additional capacity. Note that transformers with lower temperature rise ratings will typically be physically larger in size. As we discuss temperature rise, it is worth noting that transformers naturally generate heat and have hot to the touch enclosure temperatures as a result. Harmonized standards allow for transformer temperature enclosures to reach as high as 90 C or 194 degrees Fahrenheit. Instead of your hand, be sure to use a thermal scan to measure the enclosure temperature. Given the temperatures of these units, many customers ask if these transformers require a special fire-resistant room when installed indoors. The answer is that they do not. The National Electric Code, or NEC, has exceptions specifically written for transformers, acknowledging that the high ratings of the insulation class, such as 220C for ventilated transformers, protects the unit and its environment from these high internal temperatures. Inrush. There are two types of inrush values: absolute maximum inrush and practical maximum inrush. Absolute maximum inrush is the initial high peak of current that occurs in the first few cycles of energization, which can be 30 to 40 times the rated current. Practical maximum inrush is the inrush that can be seen after initial energization. This is typically valued at 1/3 of the absolute maximum inrush. Typically, inrush current is usually estimated at 12 times the rated current. But inrush can vary based on previous magnetization of the transformer and is inconsistent if you were to measure it. Due to variations in design properties, some manufacturers do not publish general inrush information, although it is available for request for specific designs. Losses and efficiency levels. Just like all other electrical components, transformers have electrical losses associated with them. These losses are measured in watts and will vary depending on the loading of the transformer as well as other factors. On the flip side, transformers will also have efficiency levels associated with them. The efficiency of a transformer is defined as the ratio of useful output power to the input power. The lower the electrical losses, the higher the efficiency. In the United States, transformer minimum efficiency levels are mandated by the Department of Energy, or DOE. The current minimum efficiency levels as defined by the DOE are shown here. Sound levels. Under normal loading and operations, transformers will have an audible sound level. This is caused by multiple factors, primarily due to the magnetostriction of the core material and other phenomena associated with the magnetic fluxes involved. Magnetostriction is the change in shape or dimensions of a material when it is magnetized. Transformer manufacturers measure and design around the audible decibel sound level for given transformers under certain load conditions. There are many standard organizations, including NEMA, that provide guidelines on acceptable sound levels per given kVA sizes. Most manufacturers have options available to provide transformers with lower sound levels than standard upon request. Sometimes pads are used to absorb transformer vibrations to reduce noise. Electrostatic shields. Electrostatic shields are conducting sheets placed between primary and secondary windings and grounded to reduce electrical interference and to provide additional protection from line-to-line or line-to-ground noise. Sometimes these are referred to as Faraday shields. There are different types of low-voltage dry-type distribution transformers that are used in electrical systems. General-purpose ventilated transformers. As the name suggests, general-purpose transformers are for just that, general purpose. These are the most commonly used transformers used to step up or step down voltages in commercial and industrial facilities to feed general loads. A common installation would be in a commercial facility that has 480, 277, 208, and 120 volt loads. In these facilities, general purpose transformers would be fed from 480 volt switchboards or panel boards and used to provide 208 volt power to feed downstream panel boards. These panel boards would then distribute power to the lower voltage loads in the facility. Also, as the name suggests, these transformers use natural air ventilation as an insulating and cooling means to protect the transformer. Hot air rises, so the natural airflow and ventilation sees air coming up through openings in the bottom of the transformer, through the core and coil assembly, and then venting out of the openings in the front and rear of the unit. It is imperative that users do not obstruct the airflow for these transformers. In addition, manufacturers are required to mark the product with minimum wall clearance requirements from the ventilated openings. These products are typically rated for indoor use with NEMA 1 or NEMA 2 enclosure ratings. They can often be converted to NEMA 3R enclosure ratings with the field installation of weather shield attachments that act as awnings over the ventilated openings to prevent falling rain from getting inside of the transformer. K-factor transformers. K-factor is a common industry term that relates to the amount of harmonics produced by a given load. The larger the K-factor, the more harmonics are present. Linear loads, for example, have a K-factor of 1. Transformers may carry a K-factor rating to define the transformer's ability to withstand the additional heating generated by harmonic currents. The general-purpose ventilated transformers described earlier have a K-factor of 1 for general-purpose linear loads. Typically, a transformer is not called a K-factor transformer unless it has a K-factor greater than 1. Common K-factors are 4, 9, 13, and 20. K-factor transformers are typically oversized versus general-purpose transformers and have other differentiating design characteristics, such as 200% neutrals, electrostatic shields, and core designs to reduce induction levels. Harmonic mitigating transformers. Harmonic mitigating transformers, or HMTs, are specially designed transformers that, when installed properly within an electrical system, will cancel out and treat some of harmonic currents. Third harmonics, or triplins, are canceled on the secondary of the HMTs, eliminating the circulating current in the delta winding of a delta Y K-rated or standard transformer. In combination, multiple HMTs can be used to eliminate most of the significant harmonic currents generated by 6-pulse variable frequency drives and other rectifiers. The simple way to think about K-factor and harmonic mitigating transformers is that K-factor transformers are oversized to withstand or live with the harmonics in the system, while the harmonic mitigating transformers can be used to cancel out or fix the harmonic issues in a system. Totally enclosed non-ventilated. Totally enclosed non-ventilated, or TENV designs, are for special applications where, due to adverse atmospheric conditions, it is desirable to have an enclosure with no openings. These applications could be environments that contain conductive, corrosive, or combustible materials that might damage a transformer or have lint and dust particles that might block the ventilation's passages. Other applications could be where the unit will be installed outdoors and open to general public access. These transformers have no openings in the enclosure. Therefore, heat is dissipated by radiating from the surface area in lieu of design ventilation. Consequently, the enclosures are larger than their ventilated equivalents. TENV designs are required when greater than NEMA 3R enclosure ratings are needed, such as NEMA 12 or NEMA 4X. Encapsulated transformers. Encapsulated style transformers are general purpose transformers whose core and coil assemblies are surrounded by an encapsulate resin compound in lieu of air. These transformers utilize TENV enclosure designs and are suitable for harsher environments. Encapsulated transformers are desirable in high vibration environments given the protective nature of the resin block, which once hardened will ensure that nothing internal to the transformer will move. These types of transformers are also physically smaller than non-encapsulated style transformers given the heat sink properties of the resin. Encapsulated transformers will typically have cable-led connections in lieu of the terminal bars you will find in an air-insulated unit. These transformers will also have tap connections in the form of multiple cable options of which to terminate customer connections. Buck-boost transformers. Buck-boost transformers are a subset of small encapsulated transformers. These autotransformers provide an economical method of correcting a lower or higher voltage. Industry terminology used to describe the regulations with these transformers include bucking when it is used to slightly lower a voltage and boosting when it is used to increase a voltage. Typically, these involve rewiring a standard encapsulated unit in a manner where you can achieve significantly more kVA output than its rated nameplate size, given the small delta in input and output voltages. Let's say you have a new light you wish to install at the end of a parking lot. This light is optimized for use with 115 volt single-phase power and pulls 2 amps. You run a circuit to this new fixture location, and due to voltage drop, you are only measuring 102 volts. You could install a buck-boost transformer to boost up this voltage from 102 volts to 115 volts. In this instance, you could provide a 50 VA transformer. Typically, 50 VA would be undersized for this load, as a single-phase 50A transformer would only be rated for 0.43 amps at 115 volts. However, when wired up to a buck-boost transformer, only making a minor voltage adjustment from 102 to 115 volts, this 50 VA transformer is now rated for 360 VA with a 3.13 amp output. Motor drive isolation transformers. Motor drive isolation transformers are specifically designed for use with variable frequency drives, or VFDs. These transformers provide electrical isolation between the incoming line power and the drive circuitry. voltage conversion of input line voltages to match the drive input voltage, offer harmonic reduction similar to a line reactor based on its impedance, and reduced short circuit currents and voltage line transients. Motor drive isolation transformers have non-typical kVA sizes versus other types of transformers, as they are designed and sized with specific VFD requirements in mind. It's important to note that when the term isolation transformer is used, that does not automatically mean that a motor drive isolation transformer should be used. Standard general purpose transformers are considered isolation transformers because their primary and secondary windings are isolated from themselves. Motor drive isolation transformers should only be quoted and applied for their intended use. Transformers are an integral part of AC power distribution systems and can be found throughout utility systems, industrial plants, data centers, commercial applications, and even outside your home. Although they have been around since the inception of electrical systems, they continue to evolve and improve with higher efficiencies in specialized applications. To learn more about transformers and to see them in action, contact us or your local Eaton representative to visit one of our Power Systems Experience Centers today.